we are Team 1, and our project was distributed joins across multiple databases. The team members include myself, Tristan Graber, Andrew Fecker, Devin Doss, and Nick Wolf. This slide is actually from the original project pitch of our original idea. We were going to implement distributed joins, specifically inner, left, right, full, and outer joins that could join two data sets uniformly housed in multiple AWS instances. We also had the goal of implementing a preview that returns a partial preview as a result of a user's query during the execution. And we also wanted to ensure that the joins worked correctly and they operated at scale. Since this, though, our project has changed a little, as you will see in the following slides.
We decided to test the performance of our single node join against a distributed hash join algorithm. So the first thing we had to do here was gather sample data, which involved IMDb data consisting of movies and movie genres where the join would occur between the movie titles and the genres. And our first step here was implementing our distributed join locally, simulating a multi-node implementation by creating multiple databases on the same node and communicating between them. We then moved on to creating a true multi-node implementation using AWS, in which we used RDS to host MySQL servers and an EC2 instance to act as a master server to communicate between the MySQL servers. Upon completing this step, we went back and looked at our performance and looked at different ways that we can improve our hashing algorithm. So here's a look at the hashing algorithm we used for our project. The first thing that you're going to see is that each server is going to hold a random list of items in each relation. Each server is then going to hash the values in its list and send that to a master server. The master server will send each server all the values that are hashed to a specific value. So now our servers will be made up of specific hash buckets, basically. This will create a single table on each server that contains all items with a specific hash value. And finally, each server will do its own join and send the master server the results that can then be concatenated together to finish the join.
The final architecture was implemented using AWS. The implementation uses the Amazon Relational Databases service to create 3 MySQL Server databases. The query handler, which was implemented in Python, acts as a master server and uses multi-threading to interact with each of the 3 MySQL databases. The application is housed in an EC2 instance and uses MySQL connector to communicate with each database. This implementation closely resembles that of a distributed database for a single warehouse. Various environment configurations were tested to determine the optimal environment for the distributed join. The baseline configuration was a test to see if the Python query handler was able to correctly communicate with the MySQL server. From there, the components were moved to the cloud. Multiple combinations of small and large cloud hardware instances were used to identify how different processors impact the time required to perform cross-RDB joins. The cross-RDB joins are implemented on a test dataset, which consists of 2 relations fragmented across the RDS nodes. After testing the algorithm's accuracy and speed of the whole table join on one server, we iteratively modified the join algorithm given the environment and compared algorithm runtimes. First, we tested a multi-MySQL join across 3 databases, hash partitioned by the join indexes. From there, we tested a single MySQL server join across the 2 relations where the relations are separated into 3 random partitions. Finally, this led us to test the complete distributed hash join algorithm and compare the runtime to those of the previous architectures.
Okay, and now to talk about some of the results that we got. For one, let's look at the orange. As you can see, our distributed join algorithm actually ran faster than a single node 3x3 join. This means that if you separate data into 3 random chunks and put those data into 3 different servers, our distributed join algorithm will actually run faster than if you put those 3 chunks into one server and did a join and union across them. Now, compare that to the red. Our multi-node 3x1 join actually was able to run faster than a single node 1x1 join. This means that if you were to pre-hash the data and put them on 3 different servers, it will run faster than if all the data was on one server and in one table. And as you can see also here, comparing the two, it takes about 3 seconds for the hashing to actually get accomplished and for the splitting to occur. Now, overall, our project was incredibly successful. The joins are correct. Each test was validated against a traditional join. They were all correct. And also our joins are very fast. Our pre-hash value or pre-hashed was faster than a traditional join, and our distributed join was faster than a single node 3x3 join. So overall, our project was successful. The only limitations we really had was that we weren't really able to accomplish our stretch goal of join previews, but as it was our stretch goal, overall, we did really well. And now to look at our demo. As you can see, as the SSH is going to, or as it's going to run, I'm going to SSH into our EC2 instance and then run the Python. This is going to run very, very quickly, as it's going to go through the entire algorithm in a very short amount of time. It's going to split up each of the data sets and then populate them all and do the join across each three. And then compare that to a traditional. As you can see here, our hash join took 4.1 seconds and our traditional join took 1.4 seconds. Now it's just comparing the two results, and as you can see here, it gave correct results. Finally, lastly, I'm just going to show you the baselines here. So it's going to be the 3x3 join. It is also accomplished. And as you can see, what's important here is that it's accomplished in 4.3 seconds rather than the 4.1 seconds. This means that our distributed algorithm runs faster. So thank you. If you have any questions, please let us know. Otherwise, thank you for watching.